Good afternoon everyone. It is my pleasure to open our Alumni Lunchtime webinar presented by Dr. Damien Guihen. Damien is a postdoctoral researcher with theme for polar technology and is based at the Australian Maritime College, University of Tasmania, Launceston. Damien is a physical oceanographer by training with a particular interest in biophysical interactions and marine sensing in the Antarctic. He studied the role that biological structures play in the boundary layer stresses in a Norwegian fjord as part of his PhD at the National University of Ireland in Galway. He then moved to the British Antarctic Survey to develop a methodology for the use of autonomous underwater gliders to undertake acoustic surveys of Antarctic krill. My name is Nicole Wilcox and I'm a proud alumna with a Bachelor of Science with Honours and also part of the Alumni Relations team at the University of Tasmania. These webinars are an opportunity to introduce you to staff and alumni who are playing key roles in research and people who are highly valued within our institution. This webinar will form a living record for the university, which you'll be able to access in the future on our website. Thank you so much for taking the time to hear from just one of our experts from the Australian Maritime College, also known as AMC, Dr. Damien Guihen. The Antarctic Gateway Partnership is a special research institute of the Australian Research Council and brings together the University of Tasmania, the Australian Antarctic Division, CSIRO and the Bureau of Meteorology in a project to develop the capacity of Tasmania's Antarctic research. The project is divided into 4 research themes, the first 3 examining the process of Antarctic's marine, ice and geological systems. And the 4th theme is focused on delivering new technology for polar science, particularly the delivery of the new autonomous underwater vehicles, also known as AUVs. In this webinar, Damien will discuss the need for autonomous observations in the Antarctic and the technological, logistical and coordination challenges that this presents. He'll also give us an update on the current state of the Gateway AUV and how the results of his fieldwork in the Ross Sea in February 27 will have an impact on future Antarctic underwater missions. I'll now pass you over to Damien.
Thank you very much, Nicole. As Nicole mentioned, my name is Damien and I'm working with a robot team working to do some Antarctic science with it. So this is, I'm going to talk a little bit about why we would use robots in the first place and why they're particularly useful in the Antarctic context. So Nicole has already mentioned that I'm working under the Antarctic Gateway Partnership, and the 4 themes, I've got them listed on the slide at the moment, covering cryosphere ocean interactions, open ocean under ice food webs, solid earth cryosphere interactions, and marine technology in polar environments. And so the marine technology is where we sit, and speaking of sitting, we're currently recording at the new lab that we have, the AUV. This is the Autonomous Marine Systems Laboratory, opened last Friday, where we also gave a name to the new AUV, and I'll talk a little bit more about that towards the end of the presentation. Within theme 4.1, we have the development and acquisition of a polar-capable AUV. Now, this is one of the most text-heavy slides that I'll use in the presentation today, but I just want to put up the text of what it is that specifically mandated. And that's the development of a next-generation polar-capable autonomous underwater vehicle. And so when I talk about robots today, mostly I'm going to be talking about these autonomous underwater vehicles. These are robots that are remotely commanded, so they're given instructions and then given a mission and then sent off on their way underwater where they autonomously conduct those missions, making decisions about navigation and collision avoidance and whatnot. So moving on to why we would use these in the Antarctic in the first place, there's a growing body of literature calling for the next generation of Antarctic science. For a long time we've had research vessels, we've had boots on the ground on ice sheets and on the continent itself. We've even had people putting tags on seals, making temperature measurements like that. We've had instruments such as profiling floats. But there's a real need, and we're seeing it through the literature, there's a real need to take our measurements of the Antarctic even further. So I particularly like this comment from Chuck Kennicott's paper, 6 Priorities for Antarctic Science, calling for the development of new autonomous vehicles and observatories that can reach remote locations. And so here he identifies the ice shelves and deep sea under ice sheets. And ice shelves and ice sheets are not things we can get under using traditional research vessels. This Seeing Under Ice workshop produced this beautiful figure of what that might look like, what an autonomous network of different types of instruments and platforms might look like. So we have, in here we have the traditional ship that has been traveling to the Antarctic for decades, using the same types of instruments that we've been using for decades. And that's very important, that's not a bad thing. These sustained measurements over many, many years are really important because doing something the same way, the same types of measurements, allow us to build up a picture of long-term time series. But in addition to that, we need to travel further under the ice, and I mentioned the seals with tags on their heads that fall off when they molt. And they're in this image as well. They're collecting a lot of valuable data. I mentioned profiling floats, and they're the little white tubes that you'll see towards the right of this image. And I mentioned autonomous underwater vehicles. We see two types here. We see a diving glider, which is a very slow-moving vehicle. I'll talk a little bit more about that in a few slides. And we see the autonomous underwater vehicle of the type that we have at the new facility here at AMC. We'll also see a few moorings in there as well. These are instruments that are put on a weight with a float, and on the string you put all sorts of temperature sensors or current profilers or whatever is needed. And then within the more recently published Antarctic Roadmap Challenges, which is really a compendium of top 10 or hit list that people want to see, researchers want to see addressed. 15% of the pages, I find it interesting to note, 15% of the pages reference these autonomous vehicles. And so what we're talking about is bringing robot engineering and of this type that happens in this building through to Antarctic science with colleagues throughout UTAS, such as other partners in the Antarctic Gateway Partnership, such as IMAS and the Australian Antarctic Division and CSIRO. Okay. And I promise that's the only cheesy animation I'll be putting in. I just had to get it out of my system, I'm sorry. So the model for this kind of interaction really is that the questions of the natural world, natural environment, come from the science community. For example, how do we understand the melt processes underneath an ice shelf? And then that gets defined as an engineering problem. So how do we get the resources or the technology in place such that we can make the measurements that are necessary to underpin those scientific observations and feed it back into the science community? So you have this virtuous circle of capability and motivation. I've thrown up a very limited list of Antarctic science questions. You ask an Antarctic researcher, what's the most important thing? You'll get very many different answers depending on how many people you ask. So a few things here, such as, is there life in subglacial lakes? Can we forecast sea ice extent, and what effect is climate change having on krill stocks? All of these things are questions that can be answered or need to be answered for the questions of societal relevance, but also of great scientific interest, and need to leverage the resources that we have in engineering. Numerical models can help. There's an awful lot of modeling work that happens already in terms of understanding flows around wharfs and flows around the shape of a ship's hull. A lot of modeling in terms of salt balances and freezing and atmospheric processes and ice-ocean interactions and glacial isostatic adjustments and models galore. But in order to make sure that these models are correct, because these are a numerical representation or an algorithmic representation of how we understand the world, in order to make sure that we have that understanding correct, we need to test them. And we test them by collecting measurements in the real world and comparing those measurements with our results of models, our expectations. And the differences we have to try and explain. Usually that means a tweak to the models. And so why that's important is if we look at some of the big questions that society is going to face over the next, in this case, over the next 3 years, in this IPCC, that's the Intergovernmental Panel on Climate Change, Fifth Assessment Report, which gives an awful lot of the science case for understanding climate change, they have an awful lot of uncertainty in their projections. In this particular figure, we're looking at global mean sea level rise, and you see two solid lines represented in the figure, running from 2000 in the past up to 2100, and they're looking at how will sea level increase over the next during this century. The two circumstances are in there because we have different scenarios, different policies might play out, the world's governments might take one approach to carbon capture or carbon emission reduction, or they might take another. In fact, there's a series of scenarios considered. But even within each scenario, there's a great deal of uncertainty, and that uncertainty is driven by or caused by our knowledge gaps in areas of processes in the natural world. So this is bits of the models that we need. So effectively, when we're looking at uncertainty in these models, these are areas that we can look to reduce by having a better understanding of the processes involved. Antarctica represents one of the largest uncertainties in mean sea level rise, for example. And that's because Antarctica is a very dynamic place. I'm not going to talk a great deal about ice shelves or the movement of ice on water or even melt, except to say that it represents challenges on a number of fronts. Our understanding of the processes, certainly. That is, how does the ocean current melt the ice? What does that do in terms of weakening the ice shelf or increasing the number of icebergs? Does that cause a risk to shipping? But also, how do we get to the places we need to go to make those kinds of measurements? And this brings me back to the figure I showed earlier. And this is why we're looking at, researchers look at the toolkit that is available, and some that aren't, and start to think about how a network of instruments and platforms need to look in order to collect the measurements that we need to reduce the uncertainty in our understanding of these processes in the Antarctic. So I said I would talk about robots, and I want to start with the word robot. These vehicles and platforms I've talked about are generally thought of as robots. But where does the word come from? I always find this fascinating. It's actually a Czech word, which means laborer, a forced laborer, robota. And it didn't come from Asimov, but Asimov popularized it in this fascinating series of short stories called iRobot. Much preferred that to the movie. And we've seen the use of the word robot increase a great deal. I don't know what happened in the late 1980s, but there was a real peak there. But we've seen an increase only in the last century of the word robot. And that corresponds with our technology developments as well. And then more specifically, robots in the ocean. Now there are a number of different strands coming together on this, and so there's no one originator of the idea of a robot in the ocean. But this is the one that inspired me. And this is a work by Henry Stommel, who is a rather famous oceanographer from Woods Hole Institute at MIT. And he wrote this paper in 1989, or published in 1989, and he called it the Slocum Mission. It was named after Joshua Slocum, first person to sail around the world single-handedly. And he postulated a world where we want to know, is the ocean heating up? And I'll read just this quick quotation from the paper. Is the ocean heating up? Where are the pollutants going? Can we construct theoretical models of the ocean circulation that are useful in predicting the direction of climate change? With a necessarily small fleet of research ships, how could numerous widely dispersed measurements throughout all depths of the ocean be obtained on a routine basis? And so this idea of a necessarily small fleet of research ships is one that's actually quite pertinent today, because we're seeing a global reduction in the number of research vessels, and to replace that, an increase in the number of autonomous systems that researchers and governments are considering. And so, but even if you had,
the peak number of research vessels, it's still not enough because we're constantly looking for increased resolution. One of the biggest gaps to our understanding is a lack of resolution. Adding more resolution means adding more points of measurement, and one ship can only be in one place at one time, and so that means you really need to find a way to be in many places at once. And so what Henry Stommel suggests in this case, in '89, was a fleet of robots controlled by satellite and monitoring the ocean from 50 degrees south to 50 degrees north. So his calculation was that that's what it would take to get the resolution he needed. I do love this quotation just on the third of his 4 pages in this paper. And then it's something that's, again, worth reflecting on whenever we think of the value of this facility in the academic and education context. And that is, there's nothing like the need to make decisions to lay bare areas of ignorance that are papered over in textbooks. And for me, this says an awful lot about the value of having kind of a leading edge facility, something that's trying to do things that we haven't done very much of before, and to push what we know about deploying these vehicles, to push what we know about the kinds of data we can get back and what we can do with them. And so that then has a feedback into our syllabus and being able to bring students along with not just what's in current textbooks, but actually to have the next generation of teaching. And so Henry Stommel's paper, and supported by a few other more technical journal notes with calculations and whatnot, led to a pot of money from US defense agencies, and that led to a whole load of robot designs, and some of which have come through to products that we now can use commercially, can buy commercially and use in the Antarctic, for example. And I have this picture of Antarctic krill up now, and this is from my past life. Previously, I was working with robots to try and find these. I won't go into the life cycle of krill for very long, except to say that by some estimates, the sheer biomass of krill is comparable to the biomass of humans. So if you had large enough weighing scales, it would be rather balanced. So there's an absolute enormous amount of this protein and marine resource swimming in the Southern Ocean in large swarms that can be kilometers long. And this is a resource that is fished. It's a resource that underpins a large amount of the Antarctic marine ecosystem. And so it's important for us to know that if we're giving out licenses as a society, if we're giving out licenses to fish in these areas, what's an appropriate catch? And the way you do that is by making measurements so that you know what the standing stock is, and you need to understand what the life cycle looks like and how it will be impacted by climate change. And so there are large questions around even just how much do we fish. So this became a job for robots, and so a robot glider in this case, of the sort that Henry Stommel talked about. In his case, he was thinking about 50 degrees north, 50 south, looking at temperature and salinity primarily. In this case, we were south of 50 degrees south, so in the Antarctic waters of 60 degrees south, in the Weddell Sea, using an acoustic instrument to try and build up pictures of where we will find Antarctic krill. So this really was a preliminary study, but with a view to rolling this out to a fleet of vehicles that can make many measurements, so you have a ship passing through, maybe it's doing a logistics run, it doesn't have to be necessarily even a science run. It deploys vehicles as it goes, and then another ship 2-3 months later can pick them up. These are slow-moving, long-endurance vehicles with the ability to collect all sorts of data, and in this case, an acoustic instrument. It's slow-moving, I mentioned. I'm going to say a little bit about why this particular robot is slow-moving and how it's able to achieve motion without even having a propeller. And this is an important point. Why would you have a propeller versus not? This all goes to what you need the robot to do. So some robots need to be fast, or some vehicles need to be fast, some need to save as much energy as they can and go very slowly. In the case of what we have in front, this is from the previous manufacturer of the Sea Glider, iRobot. It's a vehicle now made by a company called Kongsberg. And from their training manual, we can see that when the vehicle wants to change its buoyancy, it has an internal reservoir held within a pressure case. And when it wants to increase its buoyancy. It pushes oil from a reservoir, an internal reservoir, into an external bladder, and that has the effect of changing the volume of the vehicle without changing the mass of the vehicle, which, of course, decreases its density, makes it more buoyant, and it floats to the surface. It does the opposite if it wants to sink. So it has this ability, very slowly, to change the amount of oil. So what it's doing is pushing oil one way, and then stop, dive, or rise, bring the oil back in, and stop and dive. So it's really making very few changes, very few mechanical changes, and getting an awful lot of diving done. And this particular model can dive to 1,000 meters. New models can dive to 6,000 meters. So very, very efficient. And then it has wings on the side, so it's able to turn that vertical motion into a horizontal component. And so this brings me to working at the Autonomous Marine Systems Laboratory. This is the new laboratory at AMC. It's just been refurbished. People who were on campus previously might remember the green shed. So it's no longer green, it's now grey, and it's been quite an overhaul, including in this picture you'll see the I-beam which we need for lifting the new facility, the new AUV. And I'm going to talk about one of the first jobs I did during my time at this facility before the new vehicle. And I don't want to sound like I'm teasing it too much, but I'll talk about our new super large AUV towards the end. But I'm going to talk a little bit about this Gravia under ice, which was run from this facility. Gravia is a vehicle made by Teledyne, and we have a vehicle here on loan from the University of British Columbia on a collaborative agreement. And so, along with the Korean Polar Research Institute and a consortium called Lioness, I was lucky enough to travel to the Nansen ice sheet in January, February of this year. And the intention was to send this vehicle, the Teledyne Gravia, underneath an Antarctic ice sheet. And this is kind of a precursor to what we might want to do in the future. Just how far can we get under, what's it going to look like, and can we make measurements of the underside of this ice sheet. And so we traveled on the RV Aron. This is an icebreaker from Incheon, Korea, down to Jangbogo. Jangbogo is the Korean base on the peninsula. There we were able to, we tested a glider, but we also were able to ballast the Gravia vehicle, because every distinct body of water that you find yourself in has a different density, and you're going to want to make sure that the vehicle is sitting properly in that water, so not floating too high, not sinking too low. You want it really at that sweet spot, and that just takes a little bit of putting weights on and taking weights off and redistributing it about the vehicle to make sure it's balanced. This is an important point, because if it's too light, it won't sink, and if it's too heavy, you'll never get it back. But what we have in the new vehicle is the ability to change that dynamically. So the Nansen ice sheet is of particular interest because it had a large calving event last year, which is to say it lost a large amount of ice, and we wanted to look underneath to see, could we get any insight into what drove that calving? Is it an issue of water currents, or are there channels developing that weaken the structure? We really don't have a good sense of that, and so our team was part of a larger consortium that brought together measurements of ground-penetrating radar and of airborne geophysics surveys, so people flying back and forth in a helicopter, and someone walking back and forth with a sled and a radar, and us on a ship deploying instruments over the side and also trying to get this robot underneath an ice sheet. So it went there, it did get under, and so what we're looking at here is the color shows you height. I don't have a color bar in there, but the color shows you the height of the ice sheet. This is one run underneath, where you can see towards B is so this runs along latitude, longitude. So A is further west, B is further east, B is where we went under. So right at this, right at where we were able to go under the ice sheet, you can see this kind of buckling of the ice sheet. So Unfortunately, this was the only run we got to do, so we weren't able to see, was this a common phenomenon? Is this just more localized? We would like to have been able to try and map out channels, but we had some curious issues of performance with the vehicle. And I'm going to, initially very frustrating. You don't want to see your robots go wrong, but this is about development, and so we looked into why it's going wrong. Why would it not dive? It wasn't that we were seeing errors within the vehicle itself. We had done a number of trial runs, and even before, even on the day when we had the most trouble, just beforehand, we had tried to run it out in open water, and it was running very smoothly. So then we went back to the ice sheet and tried again. And perhaps no coincidence, the problems we had were when we were trying to run at the ice shelf. This meant we were trying to get down to about 140 meters, something we had no problem with in open water. But curiously, when we came to the ice sheet, the vehicle didn't error, it just refused to dive. This picture shows what the conditions in the field were like on that day. So this is taken from a small boat. You can see the robot sticking above the water about as much as it should, but you've got an awful lot of it has got an awful lot of platelet ice and panning ice starting to form right at the surface there. And so this figure is a little unclear maybe, but what I'm trying to show here is that on the 3rd of February, it wasn't, there wasn't very much in the water acoustically, but on the 14th of February, the day when we had all of these problems diving, we were getting an awful lot of acoustic backscatter. That is to say, there were things in the water that were reflecting back the sound that we were putting out from our various instruments, and this starts to make us think that maybe this is what's causing the problem. So sea ice on the surface, lots of acoustic targets in the water, maybe this is what's going wrong. So the concept then, and validated with some imagery analysis done as late as last night, indicates that we have a vehicle that we're trying to get under this ice shelf, and in order to be safe, and as part of this autonomy, so as part of its navigation, it's trying to avoid obstacles. So you don't want it running into a rock or a solid object. And so it's sending out pings of sound, like a bit like a bat, like an echolocation. This is an optical avoidance sonar. But we had this, it seems from our records now, that we had a mass of supercooled water. This is water that is colder than the freezing point at the surface. So this is ice that is just primed to freeze. And where that comes from is from losing heat to melting underneath the ice sheet. So this was actually happening quite deep down. We were getting this plume of water at about 300 meters from underneath the ice sheet. And this was precipitating ice crystals, which I can now see in photos, but also that was what was accreting at the surface and forming this rapidly forming this sea ice right at the surface. And the collision avoidance system was seeing all of this in the acoustics. So the crystals were big enough that they were reflecting sound back to the vehicle. The vehicle saw a whole lot of obstacles that were really just ice crystals, and it decided that it didn't want to dive. So the lesson for us in there is, when we're thinking about autonomous vehicles, we did two things there. We got an interesting perspective of an environment that's very hard to get to, but we also had a behavior we didn't expect. So autonomous vehicles really, and the development of them, were balancing, trying to reduce these unexpected behaviors, trying to interpret data, because a lot of the data we get is kind of novel or new perspectives or instruments used in unusual ways, and all of the technical challenges that come with that. And why we would do it is because there's a large need for it. The societal relevance is large, and we get these unique data sets and unique perspectives that we haven't been able to get before, to help us fill in the gaps that reduce our uncertainties in models and have downstream effects that help people with, say, city planners when thinking about coastal defences. So I mentioned the opening of this new facility. And so this new facility at AMC welcomed our newest AUV. And
you might not be able to see it in this image, but it's got a label at the back with its new name. And up until last Friday, we've been referring to this as the vehicle, just the vehicle. But now, thanks to the local Aboriginal community, we have a new name in Palawakani, which is Nupiri Muka, which means Eye of the Sea. And so we're very grateful to have this great name, although when they arrived to come and formally name the vehicle, the community suggested that Green Shark would have been an equally appropriate name. And so, but Eye of the Sea is a great one because this really is a platform for instrumentation and observation. And the vehicle itself is made by International Submarine Engineering in British Columbia, Canada. It was delivered to AMC in May of this year as part of this Gateway Partnership, co-investment by ARC and the Australian Research Council through Gateway and from AMC. It's 6.6 meters long, weighs 1.5 tons. When it fills with water and you want to lift it, it can be up to 3 tons. And it's got a wide variety of instruments both on it and then instruments that we can put on it into the future. And yeah, and it's very green. So this is a picture of Isaac and Conrad, two of our engineers, who are wrangling the vehicle at the moment. So this is part of the tests that were performed in July in Beauty Point, which is, for those of you unfamiliar with it, it's just north of Launceston, along the Tamar, on the west side of the Tamar, where AMC had a training facility. And it's a great place for us to get wharf access and a safe environment to work. And so this is the first place we've been deploying the vehicle. You see another picture of it. At the moment, we're lifting it in and out using these strops and a crane. In fact, I was at Beauty Point just this morning, where the team is trialing a new trailer, and so it's actually very exciting. It means that this vehicle can now be loaded onto this trailer, brought to slipways all around Tasmania, and quickly launched. So just down a boat ramp, wind it out, and now you've got a massively capable AUV in the water, in a fraction of the time it takes to coordinate the cranes. So that's the latest development as of today. The vehicle, I've mentioned some of the sensors on board, or I've mentioned that it has them. What it's measuring as standard is the conductivity, which gives you the saltiness of the water, the salinity and the saltiness of the water, the temperature, and the depth. That tells us an awful lot about the layers in the ocean, how sound will travel, how water will even move, because that we don't often think about it, but the ocean is actually quite layered. And those different layers and water masses interact in different ways, and if there's instability, for example, that can drive some overturning. And so these are all things that are measured and have been measured for decades, if not hundreds of years, using instruments of one sort or another. Beyond that, we use an awful lot of acoustic instruments. So the measurement of these layers is very important for us because we need to know how sound will travel, so that we can use that understanding to correct our calculations of range with of pings, of echoes coming back to us from these acoustic instruments. Acoustic instruments on board include the same type, or a more advanced type of obstacle avoidance system at the front, so it's able to get a picture. The vehicle, as it travels, is able to get a picture using sound of what's ahead, and then take whatever action it deems necessary. It's also got a system called interferometric sonar. Now, this is for anyone who knows the interferometric sonars. This is an EdgeTech 2205 system, and what it's doing is sending out pings in all sorts of different directions and listening to the angles and the times that it takes to come back, and the strength of those signals coming back. And so, by putting all of this information together, it can build up a picture of seabed surfaces. Now, curiously, with this particular vehicle, that system can be turned upside down. So if we want to send it under an ice sheet, we can turn that system upside down, and instead of making seabed maps, we're making maps of the underneath of the ice. It's also got a traditional side scan sonar,
or at least it's able to build up data sets of side-scan sonar, which is a standard survey instrument, and seabed profiling as well. So we can do a certain amount of profiling of the sediments, so you can see the layers under the seabed. And really the range of that depends on how deep the vehicle is, first of all, and what type of sediment is involved. If it's very hard sediment, the waves don't travel very far, the energy is lost very quickly. If it's very soft sediment, the sound waves will travel much further. And then we have a magnetometer on board as well, and that gives us information about geomagnetic anomalies, which can tell us about different rock types and geological past. And then beyond that, we have the ability to put on anything that's watertight. So if you have an instrument, for example, that is rated to 5,000 meters, as this vehicle is, we can dive to 5,000 meters, and if you have an instrument that can go with it, it's quite easy just to strap it on and let it go. Now, if you want it integrated into the vehicle, we have a way of connecting it through to the computers, even at 5,000 meters, connecting it through to the computers that are driving the vehicle and collecting the data. And we're even looking at ways of using that data to help the vehicle make decisions about what to do next. So that is, you give it a mission, send it out, and this is called adaptive sampling, and maybe it encounters a circumstance, maybe it's a certain temperature of water or a certain acoustic backscatter. It encounters this, and then it can adapt its behavior. So maybe it turns around and samples at a higher frequency, or So this is a really big area that we can really start to shape complex missions around rather technical science requirements. So that's another photo of the vehicle as it heads a little bit further out to sea. So in terms of communicating with the vehicle, what we have is at the surface we pretty much just use Wi-Fi. And that'll give you about a kilometer range. So that's good for when the vehicle has just gone in the water, you're doing your preliminary checks, you want to make sure that you're seeing as much data as possible to catch any faults. Beyond that 1 kilometer, we have a fallback to Iridium, which is a satellite system where we can send messages about location, so we can track it at the surface. And then underwater we use acoustics. And then we get about 4 or 5 kilometers of good communications underwater using acoustics, and by good I mean lots of back and forth of data. But beyond that 5 kilometer range, really we're limited to tracking. So, oops. Again, I won't dwell on this slide, there's a lot of text here, but just to very quickly put up what the specifications are of the vehicle. I mentioned a max depth of 5,000 meters. We have an endurance of 140 kilometers currently. That's a mission duration of about 26 hours. And we're set to double that by January or February when we have a new battery pack. So that's in the works. And so the vehicle is modular, which means you can take it apart at different junctures. Take it apart, put in a new section, and close it all back up again. And a battery pack is how we'll put that in. We just take it apart, slot it in, slide it together. And similarly, if there are instruments we want to use in that way in the future, we can just take it apart, put in our new instrument, and put it back together. This dynamic ballast at the bottom, I mentioned that this is a problem of having to go out and make sure that your vehicle is properly ballasted or weighted for the water that you're in. That's something we will still do for this vehicle, but we have the ability to change the ballast of the vehicle in situ, or to have the ballast change during a mission. So I'll tell you first how it does it, and then I'll tell you why you would want to do it. It does it by using a 3D printed titanium sphere. So it has this volume, a crush-resistant volume that it's able to push water into and out of. A bit like a submarine. So when you push water into it, you're compressing the air inside. You push water into it, and the vehicle becomes more heavy because it has now more mass. When you push the water out of it, the opposite is true, and it's now lighter. This gives us a somewhat unique ability to lie on the seabed. So if you wanted to stop the vehicle, most vehicles, if they start, most AUVs of this type, if they stop moving, usually we keep them slightly positively buoyant, which means they want to float just a little bit. That's for good reason, because if the engine cuts out or the propeller cuts out, driven in our case by lithium batteries, if the propeller cuts out, you want it to make its way slowly to the surface. But there are circumstances where we might want to stop the propeller spinning and stay where we are, or sit on the seabed, or even stop underneath an ice shelf and park up underneath. Maybe we want to interact with the ice or the seabed. And for that, we can suck in water or blow it out of this titanium sphere, and that to the degree of plus or minus 30 kilograms, which is quite a bit of ballast change. Some of the challenges that the team are looking at are how do you navigate under ice. Once you start getting underwater, you lose GPS very quickly. Some of the technologies that we use to correct this or to give us navigation information, like inertial navigation systems, they get less effective at high latitudes at the polar environments that we're going to be trying to work at. There are also problems with acoustics, so we're not using the Wi-Fi underwater, we're using sound, and sound has a tendency to bounce. And so if you're tracking something, you need to be able to have reliability in your tracking. And so if you have a sound that's bouncing off a complex environment, your tracking is going to be reduced. And there's also a big question about the risk of the vehicle. We're talking about rather risky missions, and so the more missions you do in advance of that, the better your understanding of the risk logs, etc., and the better you'll be able to run more complex missions with an understanding of what the failure rates are. And it'll also put you in a position where you can mitigate those risks. That is, if you're seeing a large risk in terms of a control surface actuator, you can work to replace it or to mitigate that risk, or to put in place some system whereby if that fails, it's not a critical failure. And so I talk about this kind of slow rollout towards an ice shelf, because that's the big prize here that I've been talking about, is looking at those measurements. It's not the only one, and it's certainly not necessarily the most important. There are a lot of equally important science questions to be addressed. But what the ice shelf represents for the AUV team is the mission of the largest risk and greatest complexity. And so it's at the end of this chain. So we're moving from trials. We're in the process now of moving out of these trials where the vehicle is right now in the water at Beauty Point. Next week it will be in Georgetown, moving more towards open water. By September we will have the vehicle deployed in the Bass Strait. And in the Bass Strait, it will be doing a number of diving operations and calibration operations, and a lot more of a lot longer missions. So we're intending to run this for 10, 15 hours at a time. And now, today, we've just had word of an Antarctic mission to come towards the end of next year out of Davis Station with the Australian Antarctic Division, and where we'll be seeing how far we can get along the marginal ice, which is near the ice, the bergy bits and that kind of thing, up to sea ice. This is running under sea ice, and what kind of observations can we make there, through to an ice shelf. And that's all going to be determined by how well we fare in each one of these missions, and how much infrastructure we can put in place to support the various missions, like homing beacons or support vessels, that kind of thing. So that's how things are looking there. How does a mission actually work? We get a question or a requirement of some sort. That brings us to risk analysis. Risk analysis is driven by the fault logs that I've just mentioned. Those fault logs come from doing the missions before. And the technologies, the mitigations, that could be something very simple. It could just be a checklist, or it might be a whole new system architecture. That's really a wide area. The team experience is really important in risk analysis. Is it an environment we've worked in before? Is it, that all plays a part in that risk analysis, which then goes for insurance. We have insurance, and that means we have to abide by certain rules and follow certain pathways. The team experience in that then feeds into mission planning. So this is where we actually start putting lines on a map for the vehicle to follow. Then we go do the mission with the vehicle. And that feeds back to the science requirements. But that's not the only beneficiary. So the great thing about this is that each mission we run feeds back into more fault logs. And fault logs are just records of the vehicle where maybe it tried to move a surface and it didn't move as much as it had. These are quite common things. the mitigation technologies, so things that we figured out or bought or were recommended to us or fixed along the way. We'll bring that into the future, and of course each mission increases our team experience. And so that means using this kind of process we can really increase the complexity of our missions as we approach ice shelves. I mentioned Beauty Point. Anyone who's been out there might remember the Stephen Brown, which is the moored vessel, which we've been using as a control center. We've got launch and recovery facilities from the wharf, and the vehicle has been running in this survey area. So it's a rather confined area at the moment, but as I mentioned, next week we're north of Georgetown, and then beyond that into Bass Strait. So these are just some data from underneath along the wharf, in fact, and so we can see some data from the side scan sonar. This is pings, lateral pings, and then listening to the echoes as they come back. And you can see an awful lot of debris in the Tamar just around the wharf. Apparently there were a lot of old structures in the past. And this is a map of the seabed made using the vehicle. It's an uncorrected map, so you'll see some artifacts of the actual vehicle motion in there. But this is, it's pretty fresh, so we expect to have a corrected version of all the data products pretty soon. And just for anyone who isn't familiar with the areas involved, we're currently sitting in Launch System with the vehicle, as we speak, in the water at Beauty Point, and that's where it'll be housed for the next month or so. Georgetown is the Bass Strait survey that I mentioned. We'll be running a mission in both the area around Georgetown in the Tamar estuary with some of our colleagues from IMAS, and then also in the Bass Strait out of Georgetown. And then in the future, I have it in grey. This is hopefully within the calendar year of 2017. We just don't have exact dates, probably around November. We expect to be operating in Storm Bay as well, and hopefully interacting with some of our gateway partners there too. And so that's it. We're going under the ice with this vehicle. That's what we do here. Thank you very much.
Well, thanks so much. Yes, that was great. We've got a few minutes. We've got a couple of questions, so I might pose those two if that's okay. The first one is from Dylan, and he said, considering the cold water layers that were preventing the AUV from diving in the earlier example, how do you deal with that stratification and how it affects the sonar refraction?
Yeah, that's a really important question. So I think that question relates more to the accuracy of your the ray tracing of the pings. How do we deal with it? Well, in the first case, we measure it. So you need to have. This is why for every hydrographic survey we do, and I should preface this by saying I'm not a hydrographer. I don't make maps of the seabed myself. But I do work with people, and they're damn fine people. But what we do is we make measurements of the water column to try and quantify that stratification, and then to model the movement of the sound through those layers, and then use that to inform how well or otherwise our seabed measurements are going to turn out, and make corrections as necessary. Yeah. Actually, that's interesting, because one of the things that this vehicle affords us is the ability to get closer to the seabed. So where that is a larger problem for ships, which are stuck with, if you're making a measurement of the seabed from a ship, that means your sound source and your sound waves have to travel every time all the way from the surface to the seabed and then back again. And that's, as Dylan points out, there's an awful lot of issue of refraction and that's bending of the waves due to different refractive indices. But if you have a vehicle that can get closer to the seabed and you know that refraction is going to be an issue, you can send your vehicle below all that, so your sound is traveling much less. It doesn't have to travel as far, and actually an awful lot of that dynamism in the layers is constrained to the surface, so you can reduce it by getting closer to the seabed. I hope that answers your question.
And we've probably got time for one more. This is from Tom.
I was trying to be quick.
And he was wondering why the new vehicle uses a propeller versus the previous one, which used the buoyancy system to dive for movement.
Yeah, I think it's a really important question. It goes to what you want the vehicle to do. The buoyancy systems are generally used for efficiency, and these are where you're looking for very slow movement over the course of a couple of months. Just like we have different types of aircraft, we have fixed-wing aircraft, we have helicopters, they do different jobs. Even the vehicles that I've spoken about are not, it's not an exhaustive list. There are lots of different shapes and types of vehicles depending on the mission you want. So this vehicle is a high power that is lots of electrical energy. It's got a propeller, so it can kick some real speed, and its intention is to go in straight lines underneath an ice shelf, for example, or it can turn, but it can go in straight lines and keep a constant depth, and it can track the seabed, that kind of thing, which is great. What the buoyancy vehicles give you is energy efficiency, but what they lose is the ability to travel in those nice, straight, constant depth lines, or to track seabed, because they get their forward motion from changing their ballast, or their buoyancy. And changing your buoyancy means you're constantly going up and down, which is not appropriate for every mission. So it's horses for courses, really.
Great. That probably lasts all the questions. But thank you so much, Damien. That was really fascinating insight into robots and their role in Antarctic research. And we really look forward to hearing about Mocha and the mission in Antarctic. And just a little bit of housekeeping. The whole webinar has been recorded, and we'll be sending you a link for the recording in the coming days. And thank you everyone who may have stayed up late, got up early to listen to Damien's presentation. Thank you. And thanks, Damien.
Thank you.